Hi everyone, this is Quantum Garbled Circuits. I'm Zvika Brakerski and this is joint work with Henry Yuen. This version of the talk is going to be quite skeletal. I'm going to say and explain what randomized encodings and garbled circuits are, and I will explain how we extend those notions to the quantum setting and the results that we achieve. However, I will not get into the technical details of our construction. If you're interested in learning a little bit more about the technical content, let me refer you to the video, to the YouTube video whose link appears on the slide right now. This is a talk I gave at the QIP conference last year, and it contains a little bit more information. I just felt it was silly to repeat it again, so here I'm just going to give you the highlights, and if you're interested in hearing more, please do refer to this other video. You can use the link or just search for the title of the paper with QIP 2021. So the title of our paper is Quantum Garbled Circuits, and I want to tell you what garbled circuits are, but garbled circuits are a special case of a notion called randomized encoding, which is actually very important, and I would like to talk about that first. So randomized encoding is a way to encode functions using different functions. So a randomized encoding of a function is by itself a function, which, even though it's different from the original function that's being encoded, is in some sense sort of captures the behavior of the original function in a way that I'm going to describe next. So we're going to use an example, and this example is just the parity function. So it's a function that takes n bits as input, x1 up to xn, and just computes the XOR of all of these bits. And let's consider a circuit that computes this function, and this is just going to be the XOR tree. So I'm taking n equals 4 for the drawing, but you can sort of extrapolate to general n, and I'm just taking a binary tree of XORs, and I'm going to use that to compute a function. And naturally, this circuit is going to have depth log n, and in fact, any bounded Fannine circuit for computing parity is going to have depth log n, just because all the bits actually have influence on the output of the function. So this is the XOR tree for the parity function. So what I want to do now is show you a different function, f hat, which is going to look pretty different from f, even syntactically, and yet I claim that in some formal sense it encodes the functionality of the original function f. And in terms of notation, I'm going to use this triangle to denote that one function is an encoding of another function. So let's see how we do this. So the new function, the encoding, is going to have a different syntax. In particular, while the original f has 4 input bits and 1 output bit, the new function is going to have a longer input and also a longer output. So we're going to take our original x1 up to x4 and add additional input bits. In particular, for the parity function, what I'm going to do is add an additional input bit for every wire of this XOR tree that I just described. So in addition to x1 up to x4, I'm going to have now r1 up to r7, which are additional input bits to the function, and we're going to see later how we pick the values for these input bits. Now, are you ready to see what the output of f hat looks like? Well, it's going to have 8 output bits, so just like we see here. So notice that only 4 of these output bits actually touch the original input x1 up to x4, and this function may look weird at first, but it's going to be very easy to make sense of it, since every output bit of f hat actually corresponds to a gate of the original XOR tree, including the input gates. So if I'm looking at this output bit here, x1 XOR r1, then this actually corresponds to XORing all of the inputs that are adjacent to the input gate that corresponds to x1. And likewise, if we look at this output bit, it corresponds to the XOR of all the variables, all the wires that are adjacent to this gate of the XOR tree. So this is sort of how we come up with this encoding function, which we denote by f hat. So now we have f hat, which has multiple input bits, x1 up to x4 and r1 up to r7. It has multiple output bits, and notice that, again, sort of unlike the original function f, which necessarily had depth log n, the new function f hat only has depth 2, even with sort of bounded Fannine gates. So this is going to be an important feature of this encoding function f hat, noticing that its complexity, at least in terms of depth, is much lower than that of the original function. So, I introduced this f hat, and I claim that f hat is an encoding of f, and it captures the functionality of f in some way. Now let's see, why this is the case, why I claim that f hat, in fact, constitutes an encoding of f. So we say that f hat is a randomized encoding of f, and this is a notion that was formalized in this way by Applebaum, Ishai, and Kushilevitz, if the following properties hold. So first of all, notice that given the output of f hat, it is possible to recover the output of f. And this is known as correctness, or the codability of this randomized encoding. And notice that it indeed holds here. So if I take these 8 output bits and I XOR them together, then I'm going to get the original output, which is just the XOR of all the X's. And the reason is that the R's are actually going to cancel because each intermediate wire is going to sort of be adjacent to exactly 2 gates. And therefore, sort of regardless of the values of R1 up to R7, there is a decoding process that takes the output of f hat, the multi-bit output of f hat, and produces the single bit output of f. Since this holds for every value of R1 up to R7, we say this encoding has perfect correctness. So this is the correctness property. So the output of f hat gives you at least as much information as the output of the original f, because you can recover the output of the original f from the output of f hat. Now we claim that something holds also in the opposite direction, and this is the notion of privacy or simulation. So we want to argue that the output of f hat, even though it includes like all these bits, actually does not give you more information than the output of the original f. And this is formalized using the notion of simulation, which is very common in cryptography. And what we want to say is that given x1 up to x4, we can simulate. So given the outputs of x1 up to x4, the output of f hat, we can think about it as a distribution where we set the values of R1 up to R7 to be sort of random values. Then for every x1 up to x4, we have a distribution of values that f hat can take. And what we want to show is that given the output, the XOR, the value of the XOR in this case, we can actually sample from this distribution that is obtained by sort of fixing x1 up to x4 and sampling the R values at random. And this actually means, this actually implies that if I give you the output of f hat with the R's sampled at random, then actually you did not get any more information than just getting the output of the original function f, just because I could have generated a sample that would have looked exactly the same just by sort of looking at the output, just by looking at the output f of x1 up to x4. In particular, in this case, it's very easy to see what the simulator is going to do. So, in fact, the distribution, the total distribution of the output of f hat is completely uniform, conditioned on the XOR of all the outputs being equal to f. So we can just generate like a bunch of random bits and then sort of XOR f in like the right place in order to make it so that the output is equal to the value of f. So in this case, sort of we can get perfect privacy by sort of properly defining our simulator. However, in many cases, it suffices to think about statistical or even computational indistinguishability. So rather than sampling exactly from the right distribution of f hat, I'm going to sample from a distribution that's statistically close, or even a distribution that's computationally indistinguishable from the distribution of f hat. And again, this sort of comes to capture the idea that if I give you the output of f hat, or if I give you a sample from a sample output of f hat, where the R's are sampled at random, this does not give you more information than just giving you the output of f. So in that sense, we say that f hat is a randomized encoding of f, because the output of f hat implies the output of f, and the output of f implies, in a probabilistic manner, the output of f hat. So this is sort of this very insightful notion of randomized encoding. Now, why would we want to sort of think about it? I defined it and I said, well, this implies this implies this, but what is the purpose of using randomized encoding? Well, notice that we managed to design an encoding which significantly reduces the depth complexity of the function. And this is going to be sort of pretty useful where we have a new function with lower depth, which still sort of captures the functionality of the original function. And indeed, sort of different types of randomized encodings are very useful notions for cryptographic primitives because it sort of captures the essence of the function f in low complexity. So in particular, if you want to sort of securely compute f, so if you want to sort of design a cryptographic protocol for computing f for some purpose, it would actually suffice to securely compute the function f hat, because given the output of f hat, you can compute the original output f, and you do not violate privacy. You do not get more information than you intended, and a lot of cryptographic constructions actually tend to sort of get more complex as the depth grows. So being able to sort of come up with a secure computation protocol for a low depth complexity function should be much easier than doing it for a function of arbitrary depth. So in particular, this is useful for delegation of computation, certain types of non-black box constructions, even some lower bounds in complexity theory. This is really a very useful primitive in cryptography and also in other areas. Now I want to point out another useful property of this encoding that we have seen, and this is something that that is called decomposability. So decomposability means that sort of when I'm computing f hat, I actually don't need to look at all of the original input bits together. It actually suffices for me. So once I sort of fix the randomness R1 up to R7, all I need so every output bit of f hat touches at most one of the original input bits. So we never have an output bit of f hat that needs to touch both x1 and x2 at the same time or something of this sort. And this is pretty useful because it gives you this sort of online-offline property. So even if I don't know the input yet, so I know that at some point I'm going to need to compute f hat on some input x1 up to x4, but I don't know x1 up to x4 yet. I can still generate R1 up to R7 because these are just generated randomly. And this will allow me to compute sort of what is called the offline part of the encoding. So all of these bits here, I can just compute them even though I don't know the actual input x1 up to x4 yet. And even the online part, the part that depends on these inputs, well, first of all, it's just going to be a linear function because, well, any function that just touches one bit can be described as a linear function in these x's. And moreover, this even works if if we have multiple parties and each one of them holds sort of a different part of the input. So let's say we have one party that holds x1 and x2, another party that holds x3 and x4. They don't need to interact between them in order to sort of produce the online part of the encoding. It suffices that they have access to sort of the relevant part of the randomness R1 up to R7, and then they can produce the online part of the encoding. And again, this decomposability property is quite useful. So this was sort of a brief introduction to randomized encoding, but the title of our paper is Quantum Garbled Circuits. So what's a garbled circuit? So I'm not sure that there is like one definition in the literature. To me, a garbled circuit is like a type of randomized encoding where the encoded function is actually computed in a gate-by-gate manner. Sort of like what's happening here, where sort of every bit or chunk of bits in the encoding function actually corresponds to sort of what's going on locally around a gate of sort of the original circuit that computes the function that we're encoding. So in a sense, it's a randomized encoding that is, well, both decomposable because, well, you can say the same thing for the input gates, but it actually sort of works in a gate by gate manner, and sort of the encoding contains sort of a set of gadgets, like sort of you can think of here about every sort of bit here as a gadget, and every gadget sort of corresponds to what's happening at a single gate of the original function. So this is what how I like to think about garbled circuits, and indeed, sort of the idea that we have seen here for the XOR function can be generalized to sort of more complicated gates. So for a general circuit, well, it's not going to have a tree structure for one, and it's also, but the tree structure actually is not very important here, if you notice. But you also have more complicated gates than the XOR gate. In particular, most generally, you can have a NAND gate. And for NAND gate, you need a little bit more complicated gadget. There's still going to be, like, you're still going to generate like a bunch of randomness, more than one bit now. Still going to generate like a bunch of randomness for every wire of the original circuit, and you're going to come up with sort of a complicated gadget here, a complicated local gadget that allows you to sort of translate from sort of the input values onto the output values, value of that corresponds to the gate that we have. And this indeed was sort of how the original Yao's garbled circuit works. And there's like different constructions with various useful properties. All right, so what do we do in this work? So what we do is try to take this very useful notion of randomized encoding and extend it to the quantum setting. So we give a first definition of the notion of quantum randomized encoding in hope that it becomes at least as useful as it is in the classical setting. Now, then we take this definition and actually construct a quantum garbled circuit, which is again a decomposable quantum randomized encoding. But let's talk about the definition first. So it's inspired by the classical definition, but it takes into account the subtleties of the quantum setting. So we consider quantum functionality f, and this can be an arbitrary quantum functionality. It can contain unitaries, measurements, adding ancillas, tracing out registers, and so forth. So anything that's that you can consider in the quantum model of computation. And you would want to define quantum randomized encoding for every quantum functionality. And the quantum randomized encoding is a different quantum functionality, f hat, which again has correctness and privacy properties. So the correctness property, again inspired by the classical definition, is the ability to take the output of the randomized encoding and derive the output of the original function f. And again, the syntax of the randomized encoding is different from the syntax of the original function. In particular, we allow an additional random input r. So this is just a bunch of classical random bits. And we have this additional input here, e, which is just going to be a bunch of EPR pairs. So just a fixed quantum state. And this is required when we want to achieve decomposability. So you could get some meaningful notions of quantum randomized encoding even if you don't allow this additional quantum state as an additional input to the encoding function. But in most general definition, we allow it. So the quantum randomized encoding f hat takes the original input x. We should just think about it as a quantum register. So we denote quantum registers in boldface. Some random string r and this additional quantum state e. And it produces some output, and this output can be decoded to the original output of f of x. And note that this should hold even with respect to auxiliary input. So even if the original x was arbitrarily entangled with a different value y, it should still be the case that, just taking x and y and just doing nothing with y, but computing f on x should be equivalent to the case where you take x, you compute the quantum randomized encoding, then you apply the decoding, and again, sort of look at the outcome of this entire process together with y. So even in the presence of auxiliary input, correctness still needs to hold, and this is something that did not need to be explicitly defined in the classical setting. So in the classical setting, correctness with auxiliary input just follows from correctness without auxiliary input, but in the quantum setting, we need to require this explicitly. In the case of simulation, again, when we take the output of the original function f. This is just some quantum register. There should be a process that allows you to sample from the distribution of quantum randomized encodings applied to the same quantum input x. And again, this should hold also in the presence of auxiliary input. So again, if you take an auxiliary input, if you take the auxiliary input y, and then you take x and compute f of x on it, then apply the simulator to get a sample, this should be identically distributed or statistically indistinguishable or computationally indistinguishable from the case where you took x and computed the quantum randomized encoding on it, the actual quantum randomized encoding on it, and take the outcome together with the auxiliary input. So this is the definition of quantum randomized encoding. And the next thing we do is show a construction of quantum garbled circuits, which are decomposable randomized encoding. So let me explain what our construction does. It comes in two flavors, one which achieves perfect security and one with computational security. And this is analogous to what happens in the classical setting. So let me sort of explain the properties of our constructions. And again, this is a decomposable randomized encoding, and it works in a gate-by-gate manner. So what we actually do is expand this notion of a gate gadget to also apply to quantum gates. So in terms of computational assumption, obviously, if you want to achieve perfect security, you probably better not rely on any computational assumption. And our construction with computational security relies on one-way functions, in particular on post-quantum secure one-way functions. So one-way functions which are classically computable, but are not invertible even against a quantum adversary. And if we try to compare it against sort of like state-of-the-art classical garbled circuits like Beaver, Mikali, Rogaway, we see that we have sort of the same assumptions, even just to do classical garbled circuits. Now the complexity of the randomized encoding. So notice that sort of randomized encoding, as we said, is useless if you don't sort of consider the complexity. So the whole point of using randomized encoding is that its complexity is lower than that of just computing the original function. And what we have here, so let's start with the computational setting here. So if we start from a quantum circuit, so the original function f was computed by a quantum circuit with size s and depth d, then what we get in the computational setting, so if we rely on one-way functions, then the new f hat is also going to have a size that is polynomial in the size of the original circuit and also in this lambda, which is the security parameter. So this is a parameter that determines, that sort of scales the power of the adversary that is allowed to attack our scheme. So if we're talking about 128 bits of security, actually this corresponds to setting this lambda to be 128, more or less. So we get a size that's polynomial in the size of the original circuit and in the security parameter. So the blowup is polynomial. And in terms of depth, well, again, we have sort of constant depth here. Whereas in classical garbled circuits, they have they're computable in NC0, so in constant depth with bounded Fenian circuits. Here we need to think about the complexity class QNC0 sub f, which is a class of constant depth quantum circuits, but also allowing fan-out. And this is sort of necessary because even in classical garbled circuits, you actually use fan-out, so you have to have some notion of fan-out also in the quantum case. So there's very interesting work on the power of this complexity class QNC0 sub f, but this is sort of the complexity class that we need in order to compute our randomized encoding. So this is again some notion of constant depth quantum circuits that again can compute the randomized encoding. If we want perfect security, so if we don't want to rely on one-way functions, then we still have we can still get encoding that's computable on QNC0 sub f. However, now the size, well, it scales polynomially with the size, but it scales pretty badly with the depth. So it scales double exponentially with the depth of the quantum circuit d. And interestingly, this is different from what happens in the classical setting, where the dependence on d is only exponential. So somehow in the quantum setting, we sort of take another penalty of being sort of doubly exponential if we want perfect security. So notice that there's no dependence on d in the computational setting, only in the perfect security setting. And it's sort of very curious whether this double exponential blow up is inherent or whether it's possible to get something that's comparable to the classical setting. I should mention that also in the classical setting, it is not known whether it's possible to do better, like to improve the dependence on D. This is like a long-standing sort of open question in the classical setting. This is in terms of the complexity of the encoding. The decoding itself is linear in the size of the randomized encoding. So essentially the size of the encoding is corresponds more or less to the complexity of decoding, and this makes sense because as I explained, the encoding contains a bunch of gate gadgets, and what you need to do is go over these gate gadgets and sort of apply them in order to get the output of the encoding. Another pretty useful feature of our encoding scheme, of our garbled circuits, is that again, I mentioned that we can handle any quantum input x, so x can be an arbitrary quantum state, but in the case where the input is classical, then the part of the encoding corresponds to the input. So remember, we're talking about decomposable randomized encoding. So there's this online part and an offline part, and the offline part doesn't depend on x at all, and in the online part, sort of every qubit now of the online part only depends on one qubit of the input. Now, if this one qubit happens to be a classical bit, then sort of the qubit of the encoding that corresponds to that encodes this that depends on this bit is also going to be classical. So as we said, one of the reasons why decomposability is so useful is for the case where multiple parties hold different parts of the input, and it's possible that the input x to the function contains some quantum parts and some classical parts, and the classical parts are held by quantum parties, and the quantum parts are held by quantum parties, and it's still possible for these classical parties to compute the corresponding online part of the randomized encoding, even without having any quantum capabilities. So the point is that if you're not quantum, then you can compute your part of the encoding without sort of knowing anything about quantum. So all you need is to have access to this classical random string R. So these are sort of the main properties of the encoding scheme that we get, and again, this is done by sort of extending the intuition of the gate gadgets and finding sort of the correct analogs in the quantum setting. Another result that we have in the paper is an alternative construction for quantum randomized encoding, which has some favorable properties and some less favorable properties. So in this construction, we do not have a shallow encoding, and we don't have decomposability right out of the box, although it can be added. So if before I told you that one of the main advantages of using randomized encoding is in the improved depth complexity, here we don't have this, but it does have sort of a simpler overall structure and sort of a very useful partition between the parts that are quantumly computable and the parts that are classically computable, which sort of lends itself very nicely to some applications, and indeed it's used in the follow-up work for constructing secure multi-party computation protocols in the quantum setting. We also present an example for an application, and this is a zero-knowledge proof protocol. So sort of one of the motivations that we have in sort of extending classical primitives into the quantum setting is our desire to sort of not reinvent cryptography. So we know a lot of things in cryptography, and we want to be able to extend them to the quantum setting with sort of as little interruption as possible. So just take your classical components, replace them with quantum components, and things you'd want things to work. And indeed, what we show here is that if you take a classical zero-knowledge protocol for NP and replace the classical garbled circuit with our quantum garbled circuits in the right way, then you get a zero-knowledge sigma protocol for QMA. So a sigma protocol, I should say, is a 3-message protocol where the second message is public coin. It's just a random string. And this was done before by Broadbent and Grillo. They showed a sigma protocol for QMA, but we have some. Our protocol sort of has some favorable properties, And also, I think the big advantage is that what we did was to take a known classical protocol and replace the the classical garbled circuit with a quantum garbled circuit in the proper way, and you immediately get a single protocol with the same properties in the quantum setting. So this is again like a sample application that we have in the paper, and then there are other applications that are not in the paper. So you can think about additional potential applications, and you can broadly classify them into two classes. So one is what I said before, to sort of think about the cases where we classically use garbled circuit and replace the classical garbled circuit with quantum garbled circuit, and hope that you get a quantum version of the primitive that you started from. And this is pretty useful because we know how to do a lot of things classically, and it would be good to be able to extend to the quantum regime with as little work as possible. So if you could just sort of replace the building blocks and get a working construction, that would be great. So this is sort of one class of applications, and this is actually what I'm going to talk about next. But you could also try to think about whether there are quantum applications that don't even have a classical analog and could still benefit from the existence of quantum garbled circuits. So I'm leaving this sort of kind of open-ended. Sort of one could think where a primitive of this sort could be useful. So in the first class of applications, I could mention reducing the round complexity of secure multi-party computation. So this is a task where classical garbled circuits have been very useful. So you want to design a secure computation protocol where multiple parties come together and jointly compute a function in a way that preserves the privacy of their inputs. And the question is, what is the round complexity of this protocol? And again, the classical setting, this seems to be tied to the depth of the circuit that computes the function that you want to evaluate. And therefore, garbled circuits are very useful. And you can think about using quantum garbled circuits in a similar way. And indeed, this has been done in some follow-up works. Another avenue is to think about these notions of functional encryption and obfuscation, which I'm not going to define here, but they have been extremely useful in cryptography, in classical cryptography, in the last few years. And in the classical setting, there is a very close connection between functional encryption, obfuscation, and randomized encodings or garbled circuits. But in the quantum setting, we don't know how to get obfuscation or how to get functional encryption for quantum functionalities. And it's very interesting. It's even interesting to sort of think what's a proper way to define these things. And then you could ask whether you can use quantum garbled circuits in order to sort of get you closer to these notions of functional encryption and obfuscation. And there are some obstacles and some sort of directions that you'd want to take, but sort of it doesn't work just out of the box. You need to think about it a little bit. So this is still open, and of course you could think about maybe additional potential applications. So I'm going to end here. Thank you, and again, let me remind you that there is this additional YouTube video with some more technical details in case you want to watch. Thank you very much.